All right, so today we're starting our unit on simple harmonic motion. We're going to do a lot of different devices in this unit. The first one we're going to start with is pendulums. Pendulums are basically like a swing. So you have a fixed point and you have something hanging. Maybe it's a mass of some sort, and it swings to and fro, right? So it might swing back and forth. That's a pendulum. It just swings like that. Swings. Goes to a high point, highest point, swings back and forth, back and forth. So it oscillates. Oscillations are just things that go back and forth, back and forth. Okay, so it says it's a body hung from a fixed point, so it oscillates freely under combined forces of gravity and momentum. They can swing side to side. They can bounce up and down. That would be what you call a spring. Okay. The frequency is the number of swings from the starting point back to the starting point. So these are some vocabulary words that you need to know. Okay, what a pendulum is. Okay, and it can be one of these things that swings back and forth, or it can be a spring that has some mass on it. That can then bounce and stretch. Okay, so before and after. So it can be something that swings back and forth or something that bounces up and down. Okay, so it can swing or bounce, which is a spring. So you can have a mass attached to a string or a mass attached to a spring. All right, and then frequency, which is denoted by a lowercase f, is the number of complete swings from starting point back to the starting point per second. We measure it in cycles per second or hertz. The period is the time it takes for one complete cycle. We measure this in seconds. Okay? So frequency and period are reciprocals of each other. So F equals 1 over T. Or you could say that T equals 1 over F. Either way, it's the same thing. It'll look like this in your formula sheet. Yeah, so it will look like this in your formula sheet with the F equals 1 over T. More specifically, F equals 1 over T. It'll look like that in your formula sheet. These formulas are in the back of the formula sheet underneath the heat constants that we're not really going to use this year because you did that in chemistry. So on the back where the heat constants are, all of your formulas for this unit are like that one, 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 that one. Oh, wait. And that one, and that one, and that one. Ooh, and that one, and that one. Yeah, so you have a lot of formulas. So instead of trying to figure out which formula you use, we're actually going to give you a cheat sheet for this unit. It's in your packet, and you do get to use a cheat sheet on the test. So you have your 2 labs are at the back, and then the 3rd page from the last. Ta-da! You have a cheat sheet. And so you actually have all the formulas that we're going to go over today right there. Simple harmonic motion, pendulum, and spring. It's all right there. And you can use this for any test or quiz that we have. I have a copy of them for your test already. Okay, so the period, which is T, okay, is 2 pi times the square root of the length of the pendulum, so that's the length of the string on the pendulum, okay, divided by the acceleration due to gravity, which is g. Now, that could be different on different planets or moons, okay? So on Earth, it's negative 9.81. We're not going to call it negative. We're just going to use 9.81 because it's in a square root. If we put a negative in there and your length of a pendulum is a positive number, you can't square root a negative number. So we're just going to use all positives inside of that. It'll make more sense that way. It said it should be noted this equation works for a pendulum whose mass is considerably larger than the mass of the string from which it swings. So we're not going to, if you don't see mass in the equation, mass isn't really a factor. So I wouldn't worry about that. We're not going to worry about the string mass, we're not going to worry about the mass it's hanging from. Mass is not a factor when it swings. If mass isn't in the equation, it's not a factor in the pendulum swinging. Okay? However, it is a factor for the period of a spring. For a spring, the period is 2 pi times the square root of the mass that's hanging from the spring divided by the spring constant. Okay, and you've actually done F equals negative kx before, where you're doing, this is called Hooke's law. So this is where the force that's exerted on the spring is equal to negative times the spring constant times x. X is the amount that the spring is stretched. Okay, so in case you don't remember, so force on spring, that's in newtons. K is the spring constant, okay, and it's usually a newton per meter. And X is the amount of stretch or compression, depending on what you're doing with the spring, and that is measured in meters. Okay? All right, so what equations do we need to know for this unit, or for this portion? It's for our homework and stuff. So you need to know that frequency is 1 over t. You need to know for pendulums only, these are things that swing back and forth. Okay, this is the equation for the period of a pendulum. Okay? And then you need to know Hooke's law and the period of a spring. Okay, remember that your mass needs to be in kilograms. Don't forget that your mass needs to be in kilograms, otherwise this won't compute properly. Okay? Oh, and your period is in seconds. Don't forget that either. Period is in seconds. Okay? All right, so there's a couple of worked out examples for you. I'm not really going to go over those. You can look at those. If you get stuck somewhere, you can like figure those out later, okay? Do a couple of your practice exercises and then kind of turn you loose to do the rest on your own. So let's look at practice exercises, sorry. So first one here, okay? A metronome is a device used by musicians to get the desired rhythm for a musical piece. If a metronome is clicking back and forth, so that's like a pendulum, okay, with a frequency of 60 hertz, what is the period of the metronome? Well, we know that we have our equation for frequency, right? So frequency equals 1 over t. They've given us frequency, this is F, and they want to know t. This is what we're looking for. So all you'd have to do is switch the F and the T, so you could say that T equals 1 over F. So 1 over 60 hertz, okay? And then you just stick that guy in your calculator, okay? Okay, so 1 over 60, okay? And we get that. It's like one of those repeating number things. So I would call that 0.017. seconds, and that's the period. Okay, so if they give you frequency and want the period, relatively simple. Okay, all right. Let's keep going. Let's find one that has to do with pendulums. Okay, so let's turn the page over here. All right, let's look at number 4. Danielle is pushing her twin, Daniel, on a swing that hangs from a tree branch on 2 meter long ropes, okay? And we want to know what is the period of the swing, okay? So first we need to write the formula for the period of a pendulum, okay? And so that's going to be T equals, this is for part A, sorry. T equals 2 pi square root L over G. It doesn't really matter if it's an uppercase L or a lowercase L. It doesn't. Just L, whatever kind of L you would like to write. Okay. So we know the length, okay? This is our L, okay? And we assume if they don't say they're on some other planet or moon, you can assume that they're on Earth. So then we know that G is 9.81 meters per second squared, okay? So then you do 2 pi square root 2.0 over 9.81. And you just stick that in your calculator. Oops, out of focus. All right, so 2, and the pi is right above the caret button, so second caret pi times the square root of 2 divided by 9.81. Okay, and we get 2.84, okay, 2.84. Okay, and then period is measured in seconds, so that's how many seconds it is. Okay, and then part B wants to know what is the frequency of the swing. Frequency equals 1 over t. So it's just 1 over 2.84. And so you just plug that in. Oops. So 1 divided by 2.84, and you get 0.35 hertz. Okay. All right. So now let's look at a spring question. So let's keep turning that there page. Keep going. We'll find us a spring. All right. So number 8 looks like a spring question. Let's use that guy. All right. You have a 1 kilogram mass. Oh, okay. So that's our M. Hung from a coiled spring that has an elastic constant of this. So this is our K. And it's hanging, so it's working against gravity, okay? That's working against gravity. That means something. So that's your Fg is equal to mg, okay? So then I can figure that out. I want to know the period, so I'm looking for t, okay? So first I'm going to find my Fg because it's a hanging spring. That's mg. So that's 1.0 kilograms times 9.81. And we're going to just use magnitudes. So that's 9.81 newtons. Okay? So I have that. Now, what is my equation for the period of a spring? Oh, I didn't even need to find that, did I? T equals, you're going to need to do this in your lab though, so I kind of wanted to give you an example of what you're doing before I turn you loose to the PhET lab. T equals 2 pi square root m over k. So you just plug that in. 2 pi square root. Your m is in kilograms, so it's 1.0 over, your k is already in newtons per meter, so that's good, 15.0. And then you just plug that in your calculator. 2 pi square root 1 over 15. And you get 1.62 seconds. So that's the period. All right. And then to find the mass that would be needed to cause it to oscillate at 3.2 seconds, you just work backwards. So you'd have to find m. So T equals 2 pi square root m over k, right? And so this time you have your t, but you need your m. So you're going to divide both sides by 2 pi. To get rid of your square root, you're going to square everything here, okay? And then multiply by k. And that will get you your m. So I'm going to use the same spring constant, so 15.0 times my new t that they want to give me is that, okay? 3.2 over 2 pi squared. And that will give me my mass. Okay, this is tricky to put in the calculator, okay? So you'd have to do 15, open parentheses, 3.2 divided by 2 divided by pi, okay, because it's on the bottom, squared. And you get 3.89 kilograms. Okay? All right, time to go do your FET lab.